Hello, everybody. Today I'll be telling you all about adversarial examples and differential privacy. There's some of the exciting new frontiers in machine learning research, where now that machine learning works really well, we're trying to make it very robust and reliable and able to resist anything that people can do to try to interfere with its operation. So I'll start sharing my screen. I'll check back periodically to see if people are asking questions. I'm going to spend most of this talk telling you about adversarial examples because that's a topic I've worked on the most myself. I know that some of the other speakers here, like Nicolas Papernot, Patrick McDanel, and Dawn Song, are also covering some of these topics, and I'll try to make sure that I tell you slightly different things than they did. But this is a really booming area, so there's plenty of different things to hear about it. So as an outline, I'll first tell you about adversarial examples and how people can use them to interfere at training time. And then I'll spend most of the time on the subject that I've studied the most myself, which is how people can use adversarial examples to interfere at test time. And then I'll move on to differential privacy, which is an area I got into more recently. I'll tell you a little bit about what differential privacy is, and then I'll tell you about the state-of-the-art PATE-G algorithm for deep learning differential privacy. An adversarial example is an example that has been intentionally modified to cause the machine learning system to make a mistake. And I wanted to start out by highlighting an exciting recent result where researchers at Stanford showed that it's actually possible to interfere with a machine learning algorithm by modifying input examples at training time. So what happened here in this diagram is that if you look at the upper left, there's an image of a dog that is labeled as a dog in the training set and actually used to train the model. If you look in the upper middle, there's this image that looks just like a lot of noise. That's actually been very carefully computed, and I'll explain what it was computed to do in just a second. But it's not noise, it's actually a very structured, carefully calculated modification of the image. If we scale that down by multiplying it by a small number epsilon, and we add it to the original image on the left, then we get the image on the right. To a human being, it still looks just like a normal dog. To a machine learning algorithm, it's actually been modified to have a special effect. Now, if we look at the dog on the lower left, that's a dog in the test set. And we actually don't make any change to this particular image when we present it at test time. If we train using the dog from the upper left in the training set, then we correctly recognize this test set dog as being a dog with 97.8% confidence. But if we use the modified dog in the upper right in the training set, then the machine learning algorithm no longer correctly identifies this dog. It ends up being recognized as a fish with 69.7% confidence. So in this case, we've actually been able to intentionally calculate how to change a training example in order to change the class of a test example. This is a really exciting recent result that shows that you can predictably alter the behavior of deep neural networks by changing their training data in this very subtle way. I'm just checking back to see if there are questions so far. Yeah, so someone's asking, you don't train your network with only one image of the dog. And you're right, we train the network with many different images of the dog. In this case, they've been able to change the output for this single test set dog by changing only one training set dog. There's actually, for every different dog class, there's about 1,000 different dogs. And there's about 1 million images in the data set total, but most of those images are not dogs. I actually don't know if the dog is in the top 5, but because it has about 70% confidence that the image is a fish, then we know that it has 30% confidence or less that it's a dog. All right, so that's the basic idea of examples that have been computed to interfere with the neural net at training time. Oh, yeah, so someone else has asked if the same topic applies to a regression problem. I don't, off the top of my head, know of a demonstration of interfering with a regression model, but absolutely, in principle, the same concept applies. That you could actually design training set examples that are intended to cause a regression model to predict the wrong value for some specific test time input. And someone asked if Netflix's Chaos Monkey was inspired by this. I actually don't know what Chaos Monkey is, so I would need to read about that separately before I can answer this question. And okay, someone asked, are some modeling techniques more susceptible to attacks? I'll be covering that later in the talk. So I think it might be a good time to move on to talk about adversarial examples at test time. So at test time, we first noticed in 2013, at Google at least, in the group that I was interning in, that we could actually fool neural networks by modifying images at test time. I think Christian Szegedy might have noticed this a little bit earlier, but he first asked me to start working on it with him in about 2013. Later, we found out that these techniques that we use to fool neural networks at test time are very similar to work that was done to fool spam filters back as far as 2004. So that actually answers one person's question about whether similar things exist for text. That's actually more or less what spam is. And other people in the security community, including Battista Biggio, had found that they could fool neural networks earlier in 2013. But basically, the idea is that if you have an image, such as the panda on the left, that's recognized as being a panda, you can add this image in the center that looks just like noise to a human observer. And you get the image on the right, which to us still looks like a panda, but to the computer vision system is now recognized as being a gibbon with much higher confidence than the original panda. So what's going on here exactly? Well, we're not actually adding noise to the image. Noise doesn't really confuse modern convolutional networks all that much. What we're doing instead is we're adding very carefully calculated modifications that will reliably cause the machine learning algorithm to make a mistake. And I guess this means that what we're doing essentially is we're studying what happens to the neural network in the worst case possible, where someone is actually using an optimization algorithm to find the image that it's least likely to correctly process. Why is it that so many people are suddenly interested in this topic of studying neural networks in the worst case? Well, the reason is that it's only been about 4 years now that neural nets were really good at solving lots of different tasks. Since about 2013, we've seen that neural nets are able to read obfuscated text like CAPTCHAs. They've been able to transcribe sequences of numbers from photos of addresses. They've been able to recognize faces about as well as people can recognize strangers. They've been able to detect objects and images, all at more or less human level. But before about 2013, neural nets didn't work nearly as well. And if they looked at an image and they categorized that image incorrectly, that was more or less normal. So if you told someone, I can make an image that no neural net can recognize, then before about 2013, no one would have been interested. They would have just said, well, yeah, we don't generally have working computer vision. Most images do get misrecognized all the time. And now that we've managed to get machine learning to perform about as well as humans do on naturally occurring data, now we can start studying the problem of how do we make sure that neural networks work as well as humans do, even when someone is trying to trick them, even when someone is trying to force the neural network to make a mistake. I'm going to check for questions in the live chat really quick. So yeah, one person asked if an object detector can be fooled by pixel level flipping. So I think you're asking if you can fool it by changing individual pixels. In the image that I showed you of the panda, what I'm doing is I'm changing nearly every pixel in the image, but I'm changing it by just a tiny amount. So you actually can't see that any pixels changed on the right here. But there are other strategies for making these adversarial examples where people change just a few pixels, but they change them a lot. Nicolas Papernot is the one who has done most of the work on that other strategy where you change just a few pixels. He has a method that he calls the Jacobian saliency map of building adversarial examples. And then, let's see, someone asked if I'm going to talk about the poison image. I don't know exactly what you mean. I covered that a little bit earlier. If you could ask a follow-up question with more detail about what you're curious about. Somebody asked if there's any research about attacks on generative adversarial models. There isn't very much published research. There is research on attacks on generative models. Dawn Song, who is also speaking at this conference, had a paper from her group at iClear where they described how to attack a variational autoencoder. They could make images that the variational autoencoder reconstructs as looking like completely different images. So you could take like a handwritten image of the number 2 and it would get reconstructed maybe as a handwritten image of the number 9. Someone asked, can one tailor the noise to pick a particular different class? And the one thing I want to emphasize is that it's actually not really noise, it's carefully calculated. So it's a very systematic, deterministic modification rather than noise. But yes, you actually can change the noise to pick a specific different class. You won't necessarily always get that class. One thing that people study is the rate at which attacks can succeed at giving the class that you want. And there's a question I don't fully understand about how stable the adversarial attack is. I guess you're asking if things like a Gaussian filter can break the attack. I'll talk a little bit more about defenses later on. Oh yeah, so somebody said that the poison image is carefully constructed. I'll be describing how to construct these images in a little bit. So I think right now it might be a good idea to move back to the main presentation because I'll cover the answer to a lot of these questions in the next few slides. On this slide, I actually show one way that we can actually build the attack. And it's very simple and straightforward using techniques that you're already used to from training neural networks. So when we train a neural network, we take a cost function that says how well it's doing at recognizing images. And we follow the gradient of that cost function downhill. Using an algorithm like gradient descent, we compute the gradient of the cost with respect to the parameters. And then we modify the parameters to move in the direction of the gradient. Adversarial examples are just like that, except instead of trying to decrease the cost and make the neural net perform better, we try to increase the cost and make the neural net perform worse. And then the other thing that we do is instead of changing the parameters to make the neural net learn, we change the input. So we actually compute the gradient with respect to the input of the image, or the input of the model, the image itself, rather than the gradient on the parameters. On this slide, I show you several different animations where each little grid is a sequence of images that you read left to right, top to bottom, like in a book. And I show you the way that we can take an image and gradually modify it using gradient descent, so that on every step, the probability, according to the model, that the image is an airplane increases a little bit. In the top left animation, we start with a picture of a ship, and we take 4 different steps on it until we end up with an image that is recognized as being an airplane with high confidence, according to the model. You're probably thinking, nothing changed at all. And you're more or less right. I actually can't see any difference. If you open up these images in NumPy and you take the difference between successive frames, there is actually a change. This is more or less the way that Christian originally noticed that there were adversarial examples. He was interested in finding out what would a convolutional network change in the image as you try to turn the input from one class to another. Originally, we expected that maybe the convolutional net would add airplane wings to the object, and then we would know that it used airplane wings as a feature to recognize it. Instead, what we found is that the neural network is not very stable at all, and that little tiny changes that we can barely even see will reliably turn the image into an airplane. There's 4 different animations in this slide. I turn also a car, a cat, and a truck into an airplane using this same gradient descent-based technique. And the only one where I can actually see much of a difference between the start and the finish is the image of the cat. The cat's face changes color a little bit to become kind of a darker, more metallic gray. Other than that, I don't actually see anything take on any recognizable visible features of airplanes. So that's how we make an adversarial example, basically. We solve an optimization problem where we increase the cost that the model incurs when it processes a particular image. And so someone's asking if there are any examples of real life attacks on neural networks in industry. The main one that I know of is that I have friends who've worked in the finance industry, and they say that when you actually have an algorithmic trading procedure, that you need to be very careful to make sure that other people can't infer the way that your trading algorithm works. Otherwise, they can trick you into making trades that lose money for you and make money for them. So people spend a lot of time trying to obfuscate their trades. Because the finance industry is very secretive, there isn't really anything published about this, describing it directly. And then, let's see, some of the other questions I see will be answered later in this attack, or this talk, not attack. So why exactly do adversarial examples happen? One reason that I think adversarial examples happen is actually that our neural networks are too linear. And I'll describe a little bit more about what I mean by this. But a lot of you are probably thinking, wait a minute, neural nets are meant to be extremely nonlinear. What are you talking about? Well, first off, neural nets are very nonlinear if you look at them as a function of their parameters. All the different weights in the neural net get multiplied together at different layers. And that means that if you look at the function that the neural net represents in terms of how a single parameter influences that function, you do get a very nonlinear mapping. But if you look at the way that inputs are propagated to outputs, we actually see something that looks like a piecewise linear function. Rectified linear units and max out units are literally piecewise linear. And then sigmoid units, we often tune them so that we operate mostly in the linear regime of the sigmoid. If there were lots and lots of different pieces in this piecewise linear function, then the neural net would be a highly nonlinear function of its input. But I'll show you that we can actually find surprisingly few linear pieces where the neural net just keeps extrapolating linearly forever in one direction. So in this graph, I'm showing you what happens if we take a neural net and apply it to an image of a car. If you look on the left, there's another one of these animation images that's meant to be read left to right, top to bottom. Toward the middle row, you can see there's the white car on a red background that we saw in one of the earlier slides. Anywhere left or above of that image, we've subtracted off an adversarial perturbation. And anywhere to the right or below that image, we've added an adversarial perturbation. So the extreme left or the extreme right of the animation image, we see different points in image space that we can visit. This is actually just sweeping out a line in input space. Then in the graph on the right, on the horizontal axis, I show you our position as we move along this line. On the y-axis, I show you the unnormalized log probabilities of the 10 different classes of objects in this data set. You can see that basically all of the different classes, each one plotted in a different color, either sweeps out a V-shape or an upside down V-shape as we move along this line. Very close to the middle where the training example lies, there is a little bit of wiggling around. But if you look at the big picture, they're basically all V-shapes or upside down V-shapes. What that means is that if you continue to make a change and you move further in one direction, the neural net will extrapolate linearly. Generally, as human beings, we think that it's not reasonable to extrapolate linearly forever. If you're running a hamburger restaurant and you increase the price of your hamburgers by 1%, and you bring in 1% more revenue, you don't think generally that you could increase the price of the hamburgers by 10x and get 10x the revenue. You think that whatever linear effect you've observed with a small change is going to go away if you make a really big change. But this neural net here hasn't figured that out. And that's a lot of where adversarial examples come from. If you change every pixel in an image by a little tiny amount, you've actually moved really far in input space just because there are so many different pixels. And if the neural net extrapolates linearly across that entire long distance, then several little changes that all point from the panda class to the gibbon class can turn an image of a panda into a gibbon. We can also make maps of input space where we actually see the boundaries between the different classes. In this image, I show you a grid with several different maps of input space surrounding different test examples. Every little panel in this grid represents a different test set example from the CFAR 10 data set. And on the left, I show you a little legend for this map. The FGSM direction is a particular kind of adversarial example direction that we can look in. The very center of each of these little maps is the test example itself. And as we move from left to right, we move in the direction of the adversarial example. As we move right to left away from the center, we actually subtract off the adversarial example and go away from the adversarially computed direction. I mentioned earlier that adversarial examples aren't noise. If we go up or down in this graph, we actually move in a random direction that's orthogonal to the adversarial one. So then what do the maps actually mean? What are the actual colors on a map? Well, each pixel shows you the class that the object recognizer outputs at that particular location. If the pixel is white, then the object recognition algorithm got the correct class. All of the other colors represent the other 10 classes of CFAR10. And what we see is that each one of these maps is essentially white or correctly classified throughout the left half of the image and extending just a little bit right of center. What that means is that if we don't add very much of the adversarial perturbation, we get the image correct. If we add noise, it doesn't really change whether we get the image correct or not. But if we add very much of the adversarial perturbation at all, we get the wrong answer. We also see that we don't need to move to a particular coordinate to find an adversarial example. We just need to move in the direction of the gradient of the cost. And as long as we move in a direction that's significantly aligned with the gradient of the cost, we can reliably cause a mistake. If we actually make two different directions that are both highly aligned with the gradient, we can see that we get these different shapes where it's still about half of the image is adversarial and half of the image is correctly classified. And once again, we see that it doesn't really matter the particular coordinate we move to. We just need to move in the general direction where some of these adversarial perturbations take us. In a recent paper that I wrote with some collaborators at Stanford and Pennsylvania State, we found that there's actually a space of about 20 dimensions that you can move in and find adversarial examples reliably in all of those directions. And then finally, I've repeated a few times now that adversarial examples are not noise. This is actually what happens when you add noise in both directions. Most images are just correctly classified all the time, and the noise doesn't change the class. Some of the images, you see that there's color all throughout the map. That means that the neural net is just failing to generalize to the test set in this case, and the example is misclassified to start with, and then adding noise doesn't cause it to become correctly classified. So someone asked, can adversarial attacks be done in the domain of cybersecurity? And yes, there are a few different papers on this. I'm forgetting the names of the authors of one of them. There's a paper about making PDFs that are malicious, but that are recognized as being safe. There's also a paper by Catherine Gross at University of Saarland and her collaborators about modifying the manifest of Android apps to fool a neural net that she trained to recognize malware. Someone said, this seems to suggest noise helps to protect from adversarial attacks. Is that true? And no, there isn't actually any reason to see that from this graph. So if you look at the map, let's look at this CFAR10 test example right here. If we start in the middle, the CFAR10 test example is correctly classified. If we move to the right, we end up in this green area, which means that we're not classifying it correctly anymore. Now, if we add noise, the noise can take us up or down in a vertical line. And no matter how much noise we add, we stay in the green area, so we stay misclassified. That means that the noise doesn't really help. So at least in this case, it doesn't seem like the noise gets us anything. There might be other cases, other ways of using noise that could help you, but just the obvious one of adding noise to the input doesn't really help all that much. Someone asked, how does this generalize to a data set which contains successive frames of video? Later, I'll show you something about that. I'm going to ignore questions about GANs just because this presentation isn't on that topic. Someone asked, how does this differ from Google Deep Dream? So both Deep Dream and adversarial examples are based on taking gradients of the output with respect to the input. I believe that adversarial examples came before Deep Dream, but I don't know exactly how long ago people started working on Deep Dream. The goal of Deep Dream isn't necessarily to cause the model to make a mistake. The goal of Deep Dream, as far as I understand it, is more to produce interesting artistic images. Someone asks, how likely is it for adversarial perturbations to occur naturally? And that's a pretty good question. It seems extremely unlikely. You need to have a process that's actually causing them to happen. So that can happen if someone actually wants to make your neural net make a mistake. There's also some algorithms that cause adversarial perturbations to happen in the course of running the algorithm. For example, with generative adversarial networks, you can think of the generator as a network that is encouraged to create adversarial examples for the discriminator. So they really only occur if there's a situation that is set up to cause them to occur. They don't usually occur just by chance. And I think I also just answered this question about how do GANs relate to adversarial attack. You can think of the generator as being encouraged to create adversarial examples for the discriminator. And yeah, generally we've tried training the same image with lots of different noise filters, and so far that hasn't actually caused resistance to adversarial examples. Moving on in the presentation, earlier someone asked if Gaussian noise is enough to fool the model. So just adding a little bit of Gaussian noise to an input will not actually cause that input to be misclassified. But if you make an image that consists of nothing but Gaussian noise, then we found in 2014 that that's actually enough to fool the model. And our object recognition algorithms tend to get very good accuracy when we apply them to naturally occurring data. But if you think about how often they're correct, not in terms of how many test examples they classify correctly, but in terms of how many different points in the space of all possible inputs they get correct, then running these different noise values through the network shows that they get almost every input point incorrect. I've drawn a pink box around every location where an input image was recognized as being something rather than nothing. Generally, our object recognition algorithms are not trained to have an idea that an image can be nothing. So I tried a few different ways of redesigning the network to recognize that it's possible for an image to be nothing. And none of them worked particularly well. So everywhere you see a pink box, you've made the network think that Gaussian noise is something rather than nothing. And then I also wanted to see, can I actually make the network think that the Gaussian noise is an airplane? So everywhere that you see a yellow box, that means that a single step of gradient descent was able to turn the Gaussian noise into an airplane. And that had about a 25% success rate. So I chose the airplane class because it was the hardest class. If I wanted to make the object recognition algorithm think that the Gaussian noise was a horse, then on average I wouldn't need to run any steps of gradient descent, because about 70% of noise values were already recognized as horses to begin with. We can understand what's going on by looking at essentially the direction that we move in input space. I showed earlier how neural nets tend to extrapolate really irrationally when you move very far in input space. Basically, if you can draw a line and you understand how the neural net will change as you move in that line, you can reliably get the same output class just by moving in that line starting from any particular point in space. So here I show how that works on MNIST. This is from a 2014 paper, where on the left, I show that you can figure out the direction you want to move in just by taking the sign of the weights of the image. And if you add that to any different image, you get a mistake, even though it's the same perturbation we're adding to each image. This year, there's been a very popular paper at CVPR that claimed to have discovered this phenomenon called universal adversarial perturbations. But we actually knew about this since 2014, and it's very easy to explain just in terms of the neural net being too linear. It's not anything deep and mysterious. It just says that a linear model responds to a direction rather than to a particular point in space. And finally, I've spent all this time telling you that linear models have all these problems. What about less linear models? Well, it turns out there's a network called an RBF network that's more or less quadratic rather than linear. And as you take several different steps in the input space, it will actually visit all the different classes. So here we start out with a 9 at the upper left, and we use gradient descent to try to turn it into a 0. And as you watch the animation moving left to right, top to bottom, we actually see that it does turn into a 0, instead of for the other kinds of models where when we do this kind of gradient descent, we don't get any visible change at all. After it starts to look like a 0, I switch and I ask it to turn the input into a 1. And we successfully get something that looks like a 1. And then I go through and I visit the other classes, 2, 3, 4, 5, 6, 7, 8, and 9. And we actually get something that looks like each of those. So it turns out that extremely quadratic models are not nearly as vulnerable to adversarial examples as linear models are. I think this answers somebody else's question that was asked toward the start of the presentation about whether different models are more or less vulnerable. So the good news is there are models that are a lot less vulnerable. The bad news is that these quadratic models, this RBF model that I used here, it's very shallow, and so it doesn't perform very well at recognizing normal data. It only gets about 90% accuracy on the MNIST data set, which is really easy, and a good model should get 99.5% on the MNIST data set. If we try to make the quadratic model very deep in order to improve its accuracy on normal data, it actually becomes really, really hard to train. A lot of the reason that we've been using these extremely linear models for so long is that they're easy to train. So there's this tension that models that are very easy to train are also very easy to confuse. Basically, if you can change the parameters and get a predictable change in the output, then you can also change the input and get a predictable change in the output. So it seems like one way we might be able to overcome adversarial examples is to design a much better training algorithm that can train more highly nonlinear algorithms. I think this would be a good point to check for some more questions. Oh yeah, so somebody asked if a blank image with just a poison also gets classified in this case as a plane. Yeah, it does. Basically, it's the direction of the perturbation that matters. If you can make the direction highly aligned with what the neural net responds to, then it will output the class for the direction that you applied. Someone asks, will image understanding help us prevent adversarial attacks? And I'm not entirely sure what that means. Someone asks if a different optimization algorithm besides SGD could help with adversarial examples. I think in the long run, yes, but we need to have a very different model architecture too. And so far, I haven't found the right combination of optimization algorithm and new model architecture. There's a few questions that I didn't fully understand, and I'm trying to move a little bit fast. Someone asked if non-ReLU nonlinearities fix this. So it's hard to prove a negative, right? There could always be a nonlinearity that I haven't thought of yet. But so far, all the different nonlinearities I've thought of trying, like sigmoid and hyperbolic tangent and so on, haven't actually fixed it. There's a paper with my colleague, Alex Karakin, where I believe in the appendix, I forget whether it's adversarial examples in the physical world or adversarial machine learning at scale. We described some of our attempts to design new nonlinearities to fix this. And some of them help a little bit, but they don't make extremely big changes in the performance. I've also tried going through the neuroscience literature and looking for descriptions of properties of human neurons to see if any of those nonlinearities would help. And so far, they haven't. I've implemented things like Nicole Rust's model of V1, and it didn't actually do anything to reduce the vulnerability to adversarial examples. OK, I'm going to move back to the main presentation. We also find that adversarial examples generalize across different models and data sets, that the same adversarial example will fool many different models. That means that, as Christian observed back in 2013, you can train your own model and then make adversarial examples for it and send them to fool a different model. Nicolas Papernot took this observation and used it to show that essentially you can fool remotely hosted machine learning algorithms that you don't know anything about. And he also developed a clever way of sending inputs to a remotely hosted model, observing the output, and using those input-output pairs to reverse engineer the model and figure out how to fool it. He used that to fool different remotely hosted machine learning APIs, like the MetaMind API back before they were acquired by Salesforce. And Dawn Song, who's also speaking at this conference, showed how to use it to fool the Clarify object detector. I mentioned earlier that Catherine Gross used this to fool a malware detector network. And then finally, because adversarial examples transfer to so many different settings, from one model to another, one particular model that we might think about is the model that consists of putting a camera before a neural net, the way that a robot would actually need to see the world. So most of the time, we make adversarial perturbations digitally and then apply them directly to the input of a convolutional net. But if we wanted to confuse a robot out in the real world, we need to change a physical object. And then the robot would perceive it through a camera and send the image from the camera onto the convolutional net. We wouldn't get to modify the input to the convolutional net directly. Alex showed that actually the same adversarial perturbations that work digitally also work in the physical world. if he prints out adversarial examples and takes photos of them, they confuse the model just the same as if you apply them digitally. There's also adversarial examples for RL. So I'll show you this YouTube video really quick. This is by my colleague Sandy at UC Berkeley and some of our other collaborators. So this is an Atari game called Sequest. And by applying the perturbation that you can see in the second to last frame on the right, we can actually make the machine learning model perform much worse than if it's able to perform its actions without anybody interfering. This, I believe, answers someone's question earlier about whether you can make adversarial examples when you have a video feed. So this actually shows that we've got a video feed here, and we can make adversarial examples that cause the model to choose the wrong actions. There's also some other work where people do things like try to choose exactly which frames to attack, to use fewer frames to fool the model, and different variations like that. So people have asked about different defenses that we can make. There's lots of different defenses that people have tried, like just regularization things like weight decay and generative pre-training, adding lots of noise at test time. There's also more unusual things that I've tried doing, like error correcting codes, where I have several different pieces of the model output a code, and the idea is that all the different pieces of the code have to like agree with each other to point to the same class, so it's harder to just randomly bump them in some particular direction. Luca Rigazio at Panasonic Research wrote a paper about trying to remove adversarial perturbations with a denoising autoencoder. So far, none of these different defenses have worked all that well. The best thing that we can do is actually train on adversarial examples themselves. In this plot, the x-axis is time, and I show you how a convolutional net performs over time. As you move from left to right, you see the red curve and the blue curve move downhill. Those are both measuring error on the test set with clean examples. The blue curve is if we train only on clean examples. The red curve is if we train on adversarial examples. So if we use an algorithm that we call adversarial training. The green curve that stays up at the very top, that's the error rate on adversarial examples if we train only on clean examples. So just training the neural net does almost nothing to improve performance over time. The kind of cyan curve that moves down across the middle of the plot, that's the error rate on adversarial examples if we train on adversarial examples. So training on adversarial examples actually does seem to help. The other really interesting thing is that the red curve, the performance on clean examples when we train on adversarial examples, that actually goes lower than any of the other curves. So training on adversarial examples is a good regularizer that can reduce your test error. Some of my friends and I like to compare adversarial examples to a horse called Clever Hans. Clever Hans was a horse that was trained to do arithmetic, but he didn't really know how to do arithmetic. He had learned how to read people's faces. So if you asked him, Clever Hans, what's 2 + 1? He would tap his hoof 1, 2, 3 times, and then people would look excited that he had correctly answered the question, and he would see people's excitement and stop tapping. But if you wore a mask, he wouldn't know when to stop tapping. Basically, he had learned to pick up on the wrong cues, and so he appeared to be able to do the task, but in practice, he'd actually make mistakes. In honor of Clever Hans and the analogy that Bob Sturm made between Clever Hans and machine learning algorithms that don't understand what they're actually doing, my colleague Nicolas Papernot and I named our open source library for adversarial examples Clever Hans. You can download it from the OpenAI GitHub account. It's the Clever Hans repository. And this gives you a standard way of making adversarial examples and also implementing adversarial training, so that if you want to write a research paper about adversarial examples, you can be sure that you've created very strong adversarial examples with a reproducible implementation. So far I've talked a lot about adversarial examples and how you fool a neural network by changing its input. There's one other thing that people can do to try to interfere with the way we'd like to use neural nets, and that's to try to recover the training examples when we wouldn't like them to do. So imagine that we have 2 different randomized training algorithms that we apply to 2 different data sets. One that contains my data and another one shown in the lower row that does not contain my data. If somebody inspects the output of these two different algorithms, we'd like them not to be able to tell whether I was included in the data or not. If we can guarantee that it's very unlikely that anyone could inspect these algorithms and tell whether my data was there or not, then we know that my data didn't really change the outcome of the learning process at all. And so my privacy was protected. This basic idea of how to examine two different hypothetical algorithms and see the differences between them, it's called differential privacy, and it was introduced by Cynthia Dwork in 2006. So we'd actually like to apply differential privacy to deep learning. There are several different ways of doing that, but Nicolas Papernot and some of my other collaborators and I developed a technique that we call PATE, for private aggregation of teacher ensembles. The basic idea is that if you start out with some kind of data that you don't want to publish to the outside world, you can divide it up into several non-overlapping partitions. And then you train a different network to classify each of those subsets of the data. When you have several different teacher networks, if they all agree on how to classify a new point, then we know that their classification doesn't come from any particular feature of any one training example. Because if the teachers agree and no two teachers saw the same training example, they must have found some universal pattern that explains the reason for them to agree. So this gives us an intuitive way of seeing that we actually have an algorithm that gives differential privacy guarantees. This allows us to publish the classification ideas when the teacher agrees on how to classify a test input, but it doesn't let us publish the model yet. You could still examine the individual teachers and figure out what data they were trained on. To solve that, we use something like distillation. We make a new student network, and we train the student network using public data inputs to mimic the outputs of the whole ensemble of teachers. After you've trained the student in that way, it's safe to publish the student because the student never saw any of the private data. It only saw public data and the privatized votes that came from the teachers. If we then go ahead and measure the probability that a person who inspects the model can determine which of the two data sets it was trained on, and we also examine the error rate that it gets when classifying new data, we find that our model does much better than previous approaches to providing differential privacy for deep learning. So we've got an algorithm that can provide really strong privacy guarantees, and it can also classify test examples very accurately. You don't need to give up very much to add privacy to your algorithm. Overall, I guess the theme of the talk is that now that machine learning works really well, we'd like to make it robust to all the different ways that people can try to interfere with it. We've seen that adversarial examples can occur at both train time and test time, and that adversarial training gives us a partial defense against adversarial examples. We've also seen that people can try to inspect the weights of a model to recover training examples, and we can defend against that too using the PATE algorithm and also the PATE-G extension of it. I'll flip back and look for questions now. So someone asks, are the teachers in the PATE framework networks? So yes, in the version that we implemented, the teachers are deep networks. Yeah, someone says, too short on differential privacy. Could you elaborate a bit more? Yeah, I'm sorry about that. I tried to make sure I got through all the slides because I know some people might want to leave before the end of the question session. So yeah, let me go back and talk about differential privacy a little bit more. Imagine that we have some kind of very sensitive training data, like for example, medical data. And we want to train an algorithm that can process the medical data and do things like diagnose patients. We'd like to open source that model and share it with lots of different doctors throughout the world so that everyone can use it for free. But we don't want someone to be able to analyze the diagnostic network and recover the records of individual people who were in the training set. The idea of differential privacy is to make it so that the learning algorithm produces more or less the same result, whether or not any individual person is in the training set. That way we've guaranteed that it's extracting general patterns rather than memorizing features of an individual record. Someone asked, how does adversarial networks differ from generative adversarial networks? Basically, adversarial networks is a term that people use that hasn't really been defined anywhere as far as I know. I think when most people use it, sometimes they are referring to generative adversarial networks, and sometimes they're just referring to the general principle of having two networks that compete with each other. For example, there's also domain adversarial networks that are used for domain adaptation. And so people might use the phrase adversarial networks to refer to both domain adversarial networks and generative adversarial networks. Someone asks, how would you apply the teacher-student model of differential privacy to app development, in the sense of app companies like Uber taking user private data for their use? So Uber doesn't publish their machine learning models, and that means that they don't necessarily need to train the model itself with differential privacy. This is more if we have a model that we want to publish, that we would be interested in making sure that people can't analyze its weights. Uber probably has all kinds of models for predicting demand and things like that, but because they stay internal, they don't need to worry about people inspecting them. Somebody asks, what's the optimal ratio between the number of teachers and or number of prof and the number of ANN layers? I actually don't know what they're asking about exactly there. Yeah, so someone says, what about using GANs in order to create a data set versus differential privacy? So if the GANs were used to create a data set and then train on it, you could say, well, then maybe we're not going to leak information about anything that matters because the data set came from a GAN. The important thing is the GAN had to be trained on something. So you need to have some kind of differential privacy guarantee for the GAN itself. Zaffarali asks, could you go over what the student does again? So the basic idea is after we've trained all of the different teachers, the teachers can vote on a test example, and it's safe to publish which output class won that vote. So that way we can have the teachers vote and tell us what a particular example is. It's not safe to publish the weights of the teachers, though. So we can publish classification results that come out of the teachers, but we can't actually publish the weights themselves. If we want to actually publish a network that people can run on their own, instead of always asking us to classify test inputs for them, then we need to bring in the student. The idea is we take maybe about 1,000 examples that are labeled by the teachers, and we train the student to replicate that labeling. Then we can go ahead and publish the student because it was never trained on any private data. And so people can actually run the student in their own computer, and we don't need to worry that they can analyze the student and recover anything from the test data, or the sensitive data. I'm scrolling back to look at Philowan's earlier question. I don't have a further follow-up than what I said already. Yeah, and so Ramiro asks, model ensembles trained with non-overlapping subsets gives better data protection. Yeah, that's the core idea. You should read the paper itself to find out some more of the details. It's also important that when the teachers vote, they need to vote using a special noisy voting mechanism so that it's harder to reverse engineer which teachers voted for what. If you use that whole system altogether, then you get privacy guarantees. So yeah, somebody's asking, if you use a GAN to generate a data set and then you train on that data set, can you actually recover the original data? Well, we don't know of an algorithm that can recover that data for sure, but we don't have a proof that you can't do it. So if you actually want to provide a guarantee, you'd need to have such a proof. Somebody said, which paper was that? I think they mean, which paper was the PATE-G algorithm in? I'll go ahead and post a link to it in the chat. There's the link to the paper in the chat. Somebody asked if reinforcement learning could be helpful to recover from adversarial attacks. In principle, maybe it could. It's not obvious exactly what you would do to accomplish that. I guess there was the YouTube video that I showed earlier where we were able to make adversarial attacks against reinforcement learning algorithms. So they seem to be equally vulnerable compared to supervised learning. And someone asks, how would you proceed to learning about differential privacy, both in the applied and the theoretical sense? The moment, I don't know of a great universal introduction to differential privacy. I don't know of like a textbook that would tell you how to do deep learning with differential privacy. I'd suggest maybe reading the paper that I linked to. And you could also download our code. It's actually open source, so you could tinker with it and see how things like changing the number of teachers affects the performance and so on. And someone asks, do input transformations help, like scaling, warping, color, and so on, for resisting adversarial examples? And essentially, so far, we haven't really been able to find such a transformation that consistently helps. Sometimes if there's a specific adversarial example and you transform it, then it no longer gets classified correctly. But if the adversary who's creating the adversarial example knows that you're going to use that kind of filter, then they can always make an adversarial example that fills that filter. Someone asks, what does FGSM mean on the slide for mapping adversarial example and cross sections? That stands for fast gradient sign method. So yeah, I'm sorry that I didn't remember to change that slide. I actually tried to remove some of the more low-level details from this presentation to make it move a little bit faster, so I can also cover differential privacy. The fast gradient sign method is a technique that I developed in 2014, where you make an adversarial example in just a single step. You take the gradient with respect to the input, and then you take the sign of the gradient. So everywhere the gradient is positive, you output +1. Everywhere the gradient is negative, you output -1. And then when you actually add epsilon times that map of +1 and -1 values to the image, you get an adversarial example quite a lot of the time. Someone also asked about input quantization. So there's a general technique that we call gradient masking. Gradient masking is anything that you do that tries to get rid of the gradient itself. So if you, for example, pre-process the input with a staircase function so that it's flat everywhere, then there's not really any gradient anymore. But also the decision boundaries haven't really moved at all. So if you use the transfer strategy to make adversarial examples, suppose that you make some model that uses a staircase function on the input to get rid of the gradient. What you could do is you could take a different model that you train that doesn't have any staircase function at the input, and you could make adversarial examples for that model. It still has gradients, so you can actually make them. And then when you apply those adversarial examples to the model that has the gradient pre-processed out, it'll still be incorrectly classified. Someone asks, can you create adversarial examples without access to gradients? And yeah, so basically you do that by making adversarial examples for your own model. There's other tricks that you can do, like you can just take the average example from one class and subtract off the average example from another class. That gives you a direction that will very reliably turn things from into the class of your choice. Someone asked, are adversarial examples limited to images currently? I showed a video earlier in the presentation where for video data for Atari games, you can actually attack that. It's also possible to do things like adversarial examples for text. There's a paper from Stanford about that recently. And for audio, there's an idea very close to adversarial examples. It's not exactly the same thing, but more or less the same key idea. There's a paper called Hidden Voice Commands. Okay, so I think that more or less wraps things up. Thank you everyone for attending, and thank you for all the great questions. It's really been a pleasure presenting to you, and I hope you all go out and do great things in the field of adversarial machine learning. Have a good day.